Hello, and welcome back to my third project talking about important manufacturing techniques that I have learned in my class. I am Joseph Walter under Dr. Hassan Rashidi in fall 2024. So let's get into it. So first, we'll be looking at our agenda. We'll start with our first topic, which is direct extrusion, and our subtopics will be, a summary of what the technique is, applications of it, reasons why it's important, as well as capabilities and limitations. We'll be going through these subtopics for our 5 topics total, and we'll be looking at thread rolling, milling, deep drawing, and surface grinding, and then taking a look at my resources as well. So let's get started with direct extrusion. So to summarize it, a heated billet, which is kind of this main material here, is pushed through a die to create a continuous profile. The billet is often heated between 350 to 1300 degrees Celsius, but that definitely depends on the type of material used. Materials like aluminum are much lower versus steel, which is much higher. The billet and the ram would be this pressing stem here, move in the same direction, which does create friction, and it works with metals, plastics, and ceramics to create complex shapes. Looking at some applications, we have a video over here on the right of the extrusion process in action as well. So for applications in construction, it can produce aluminum window frames and structural beams. In automotive, it's used for engine blocks and radiator tubes. In the aerospace industry, it creates strong parts like airframe sections and fuselage components. And then in consumer goods, it makes items like electrical conduits and other household fixtures that are commonly used. So why it's important, it enables production of complex cross-sectional, symmetrical or similar cross-sectional profiles that are difficult otherwise. It offers a fast, high-volume production. We saw that video in the last slide that was kind of like really quick, just pushing it through. And it's also cost-effective. And finally, it minimizes waste because it's just shaping the materials. You really don't need to machine or cut away any other excess material. And lastly, for the capabilities and limitations, it's capable of producing, again, long continuous shapes. It allows for tight tolerances and good surface finish based on the kind of die you use often. It can also accommodate various material alloys for different properties. Again, we talked about aluminum and steel, but you can do all sorts of different materials. And the limitations are extremely important to talk about. There is a high friction force that's generated between the billet and the die, and as well as the press. There's also a large force required to kind of force that metal through. You're limited to only uniform cross sections, so if you want variation, you have to use a different technique, and the die wear can be significant, so you may have to replace these parts after semi-frequent use. Now I'll be moving into thread rolling. I think this is a really cool process. To kind of summarize it, the threads are formed through cold processing, so you don't need to heat the material at all, in which the material is pressed between 2 dies without cutting. You can see that over here on the right, we have the moving cylindrical die, the workpiece in the center, and then another die on the other side to kind of like roll around and create the threads in the middle here. The threads are stronger compared to machined versions of creating threads, which I think is super key. It has to do with like the way the stress works out and how continuous the grain is in the material. It also produces fast and efficiently, which is ideal for high volume production. And again, there's minimal waste of material since you're not cutting away anything and you're really just reshaping the piece. And it's common for making bolts and screws. So we can see in this process here on the right that we have the thread rolling in action. For the automotive, it produces engine bolts and suspension components often. In aerospace, it creates that turbine blade fasteners and airframe bolts. Construction, again, manufacturing threaded rods and anchor bolts. And medical devices, even creating threaded connectors for surgical instruments. So often seeing in these fastener pieces. Over here on the right, we can see the two dies moving on either side of this workpiece, and then when it pulls away, we see the threads. Why it's important, work hard materials lead to increased thread strength. I kind of talked about this earlier with how the grains stay consistent. It's much better than machining them. It results in smoother threads with fewer defects, and as well as achieving tighter tolerances for thread dimensions. For capabilities, it can produce many standard forms, like metric and imperial standards, just depends on those moving dies you use. And they also last longer because it's a cold forming process. And it often eliminates the need for secondary operations because it's ready to go how it's designed. Limitations: it's not suitable for all materials like brittle cast iron and non-ductile materials, and size of threads is limited by machine capacity, and it's difficult to form non-standard thread shapes. Moving into milling. Milling uses rotational cutters, we can see here, to remove material from a workpiece. It's capable of creating a wide range of shapes and sizes, and with CNC machining, offers high accuracy and good surface finish. And CNC is that automation of machine tools using program commands. So applications, we have aerospace, milling turbine blades, wing structure. Automotive can make many parts in the engine and transmission. Medical can create implants and other instruments. And for tooling, it can produce the actual injection molds and stamping dies, so it can be used for other processes. In this video, we saw face milling. We also saw end milling as we were going through this. So why it's important: it's suitable for both small and large production runs, so prototyping too. It works with a wide range of materials from metals to plastics, composites, etc. And you have a wide range of cutting options. We showed face and end milling. There's also slab milling and routing, many options there. Lastly, with the capabilities, you can work on multiple axes for really complex parts. You can have complex cutting paths if you want intricate designs. And there's even in-process measurement for real-time accuracy, so you can adjust as you're going. Limitations, however: the tools can wear out, especially when you're using harder materials like steel. It's less efficient for large scale, just because it's not as assembly line workable, and it also can be time intensive for those complex parts. Next, we'll go into deep drawing. So it converts flat metal sheets into 3D shapes using a punch and die. We can see that here. Here's the punch, here's the die that holds it, and then the actual blank you use. It involves radial flow, so you're moving in towards the die here, and it prevents folding and maintains uniformity. It can create complex shapes, which may require several drawing stages to prevent deformities, and it works best with ductile materials like aluminum. Applications for deep drawing include in the automotive industry. You have manufacturing car body panels. And packaging, it can be producing beverage cans. Kind of see that over here on the right. We're producing some sort of hollow shape, not a can though. In aerospace, it can make aircraft fuselage components, and in households, fabricating kitchen cookware and sinks. So reasons why it's important: it has high production rates, which makes it ideal for manufacturing. It produces durable components with high structural integrity, and its efficient use of materials reduces waste compared to other forms like stamping or punching, where you have excess material and you don't know what to do with it. And then enables production of large parts without needing to join it with something like welding. And capabilities: produces smooth surfaces, little need for finishing, can do a wide range of thicknesses, and creates lightweight parts without losing their structural properties. Limitations: not suitable for hard and brittle materials. It requires very precise tooling, which can be costly to set up, and also can cause material tearing if not properly done. So into our last topic, which is surface grinding. To kind of summarize that, it provides a high precision and smooth finishes, as well as improves flatness and dimensional accuracy. It reduces surface defects and imperfections, and it's essential for producing parts that fit together correctly. We can see over here in this diagram that usually we have a grinding wheel here, and the workpiece below it that's getting worked on, and then a shiftable bed using some dials that we'll see in the next slide. For the applications of surface grinding, you can see in the video here someone moving it back and forth to kind of get that smooth surface. For hydraulic components, really important to have smooth surfaces for good sealing and cylinders. For tools, it can be used to sharpen and finishing those cutting tools. Automotive, again, precision finishing of engine components to make sure they fit together tightly. And then aerospace, again, smoothness on turbines, so they have good properties, and landing gear. Reasons why it's important: it improves part durability by reducing surface flaws, prepares surfaces for coatings and other secondary finishing processes. It also enhances safety. I think this is the most important by far, by removing sharp edges or burrs. It should be very smooth to the touch. It also improves material compatibility when you're assembling it in a larger design, especially with different materials. Some of the capabilities of surface grinding include achieving a mirror-like finish on products. It's also capable of working on hard materials, even like hardened steel. It also allows for precise control of thickness for delicate parts. The limitations, however, though, that it's limited to flat or simple surfaces. Complex shapes are almost always challenging. High material removal rates are really difficult, and then it requires a skilled operator to avoid surface defects such as burn marks or cracks as well. And then here are just some of the resources I used. Just moving through those. I want to thank you for watching my video. This is a disclaimer. This is for educational purposes only, and there is no intent of copyright infringement. Thank you.